afternoon, everyone. Uh, this talk would be on algebraic connectivity and Fiedler vectors. So, as I defined in earlier class, you know what is algebraic connectivity? That is the second smallest eigenvalue of the Laplacian matrix. And we'll also discuss about its corresponding eigenvectors and then how they are related to graph structure. So outline of the talk would be algebraic connectivity and certain properties, and then I'll go for Fiedler vectors and how it's related to graph structure. As an application, I'll tell about spectral drawing, and then some related problems we'll discuss. So one thing that this is necessary here, and the three fundamental operations we use in graph theory, and those are one is union, that is I'm considering here disjoint union. One is join, and another is complement. So all three I think you are used to. So union is just disjoint union means two graphs with disjoint sets of vertices you are taking, and then the union is you have to take a copy of G and copy of H. So that's the union of G and H, that graph. And the join is you have to take the union basically. So first you take union of G and H and then put all the possible edges between the vertices of G to vertices of H. That's the join. And complement is you have to take the same vertex set HG, and then which edges are not present in G, those edges you will take in complement and vice versa. So these are the three graph operation. And if I take the eigenvalues, Laplacian eigenvalues of G as 0 and lambda 2 to lambda n, and for H, I'm taking the Laplacian eigenvalues as 0 and mu 2 to mu m. So G is a graph on n vertices, H is a graph on m vertices. Then we can express all the eigenvalues of Laplacian eigenvalues of union, join, and complement. For union, because you are taking two disjoint graphs, so you will just take the union of the eigenvalues, and your order in the union is basically n plus m. So you will get these many eigenvalues. So these are all the eigenvalues of the union. If you take join, so in case of adjacency matrix, it's difficult to say like the eigenvalues for the join. But for Laplacian, you can get the eigenvalues as this. And for complement also, you can get the eigenvalues from G for G complement. Those will be like this. And these can be obtained because the matrices will look like this. So if I'm taking the eigenvectors for G as xi, corresponding to lambda I, and yj, the eigenvector for h corresponding to mu j. So this way we are considering. Then your Laplacian matrix for union will just be a diagonal matrix, block diagonal matrix. So you can just take the eigenvectors as xi and put 0 below. So in the first part you take xi, which are the eigenvectors for Lg. So you form this vector that will work as eigenvalue corresponding to lambda I for union also. So taking such eigenvectors, you can get the spectrum as I told. And then for join, actually the matrix will look like this. Oh, sorry, here plus is missing. So it will look like Lg plus m times identity will be added because you are putting all the edges. And then here you will get the all ones matrix with a negative sign. And similarly, so here you can take the eigenvector all ones vector that will give you 0. And you can take xi and 0 or 0 and yj, this kind of vectors from 2 to n or 2 to m, and they will give you the eigenvalues which will look like lambda I plus m and mu I plus n. And the last eigenvector that is value that is coming as n plus m, that will come from the vector which you can take in this way. Okay, so this will produce the spectrum, and the spectrum of complement that is looking like n minus eigenvalues of G. That's because of this. LG plus LG complement, you can observe that that is giving you the Laplacian matrix of the complete graph. So these three spectrum I'll use, that's why I mentioned. So you can just remember how it's happening. So now knowing this, first thing is this already we have observed that if we are taking a disconnected graph, then multiplicity of 0 as an eigenvalue equals to the number of components. So if the graph is disconnected, obviously algebraic connectivity is 0. And otherwise, like means in that case will not define as algebraic connectivity. It's a 0, second smallest eigenvalue is 0. Okay. And this thing can also be obtained because of this complement and join operation already I have told. So lambda and the largest eigenvalue is always less than equal to n. So eigenvalues um, uh, of a graph, Laplacian eigenvalue, they lie between 0 to n. So lambda n is always less than equal to n. This you can prove. So, like you were online, otherwise I would have asked how this is happening. So lambda n will be less than equal to n. Okay, and lambda n will be equal to n if and only if G complement is disconnected. So this is clear because if I'm taking lambda n equal to n, then G complement is disconnected, that I have to show. So lambda n is equal to n, then you can observe like uh, from this actually you can observe that lambda n equal to n, then your in the G complement this eigenvalue, this is becoming 0. Okay, so G complement has 2 zeros, so that means G complement must be disconnected. And the other way, if you are taking like G complement is disconnected, then you have to show that lambda n equal to n. Then G complement is disconnected means G must be a join because it's a G complement is disconnected. So in G you are putting which edges are missing. So then it will look like a join of two graphs. So in that case, basically this will come. So that's a if and only if condition. So lambda n is always less than equal to n, and it will be equal to n only when G complement is disconnected. In that case, basically G is a join of two graphs. Now, if I consider a tree, we can tell more. And in case of tree, like we can say that algebraic connectivity will be less than equal to 1. And equality will hold only when it is a star. So star, you know that it has a central vertex with degree n minus 1, all other vertices are dependent. So and that is the thing. So to show AT is less than equal to 1, you have to know what is vertex connectivity. Vertex connectivity is the minimum number of vertices required by deletion of which the graph becomes disconnected. In case of tree, actually the vertex connectivity is 1. And this is a relation that you can follow this paper. So you can prove it also. So algebraic connectivity is always less than equal to vertex connectivity, and that is less than equal to edge connectivity. Edge connectivity is similarly defined. That is the minimum number of edges required to means minimum number of edges required to means if you are deleting those edges, the graph becomes disconnected. So that is the edge connectivity. And so here, like vertex, if you for the tree, actually deleting one vertex, you can disconnect the tree. And similarly, deleting one edge, you can disconnect the tree. So on the edge connectivity as well as its vertex connectivity becomes 1 for a tree. So this algebraic connectivity always less than equal to 1 for a tree. And in case of star, uh, spectrum is this 0, 1, 1, n. So for star, it becomes 1. So exactly 1 when it is a star. Basically, when it is a star, we know the spectrum, so we can say that it's exactly 1. But I would like to ask you as homework that if it's not a star, so that it is less than 1. So that is the converse part. So if it's a star, then obviously it equal to 1 because we know the spectrum. So now I'm asking if it is not a star, that means like if AT is less than this equality doesn't hold, you will show that this is not a star. So that I'm asking you as a question. So this is the result, that AT would be less than equal to 1, and equality holds only when, means if and only if it is a star. Now, for tree case, as I told, algebraic connectivity is much more related to how the graph structure is. Means how much connected it is. So if you observe here, like for star case, already we know the spectrum, and there the algebraic connectivity is 1, and it can be proved that the algebraic connectivity for path is the smallest one. So in tree case, the path takes the algebraic connectivity, which is the minimum, and the star takes the largest algebraic connectivity. Okay, so that way, like you can see that uh, path is comparatively, like it's not having large degree vertices, and here star is having a like n-1 degree largest degree vertices. That way it has been connected. Not only that, this result tells that algebraic connectivity is always less than equal to n by n-1 delta g, where delta g is the minimum number, minimum vertex degree. Okay, so this result, like proof is, it depends on another result. You can see the proof if you want. This is a bound for algebraic connectivity in terms of the minimum degree and n. The proof is there in Bapasar book, you can see. But this result actually tells much more, because if you, this is delta g is the minimum degree. So if the graph has a vertex which is a pendant vertex, you can say that AG is near to 1. Okay. So depending on this, so larger degree vertices are there and your delta G is, let's say, 3 or 4. Accordingly, you can say that algebraic connectivity will be more. So this is like one kind of. There are also lower bounds are there in terms of edge connectivity and all. So that way, like it reflects that if you have larger degree vertices or more edges are there in the graph, your algebraic connectivity is more, and it's less if graph is not much clustered like that. So this way it's related to, like if you look for, then it's related very much to the graph structure, how it is. Now look at the eigenvectors corresponding to the algebraic connectivity. Those are known as the Fiedler vectors. So if I take a graph and the n vertices are there, let's say x be a Fiedler vector. So I'm taking the components as x1 to xn. Now we already know that 0 is one eigenvalue for the Laplacian matrix. So and its corresponding eigenvector is the all ones vector. So I can choose my other eigenvectors perpendicular or orthogonal to all ones vector. So if I am taking a Fiedler vector, I can say that it's a vector orthogonal to 1, all ones vector. So summation of xi is 0. So that means that it has some positive entry. If some positive entry is there, there are some negative entries also there. And some zero possible zeros can be there. So if I look at the coefficients, some positive coefficients are there, negative coefficients are there, zero may be there or may not be there. So a Fiedler vector will look like this. So it cannot be entirely positive vector or entirely negative vector. So it will be like with positive and negative entries both. Now, because these are n entries, n coefficients, and I have also n vertices. So I can index those, like you can think of like giving weights to each vertex or that way. So I can label these and like coefficients to my vertices. So 1 to n, I'll just put 1 corresponds to x1 and n corresponds to xn, like that. So it gives a labeling for the vertices. And we say that like ith vertex is getting labeled with xi, and ith vertex will say positive if xi is greater than 0. And I'll say that ith vertex is negative if xi is negative. And accordingly, if it's 0, xi is 0, then I'll say that ith vertex is a 0 vertex. So accordingly, my vertices in the graph, I'm saying that they are positive, negative, or 0, depending on the corresponding coefficient in the Fiedler vector. So we are starting with any Fiedler vector, means a vector corresponding to the algebraic connectivity. So then we can name as like corresponding to that vector x, I can say which vertices are positive in the graph, which vertices are negative, which vertices are 0. And then I'll take two sets. One set is V plus. V plus contains all the vertices which are positive. That means corresponding xi, non-negative. So corresponding xi is greater than or equal to 0. Similarly, I'll define V minus that contains all the vertices which are less than equal to 0. That means negative or 0. So its corresponding xi is basically less than equal to 0. So then, like, for example, you can see here, this is a tree, and I have taken the Fiedler vector. This is the algebraic connectivity. You can compute using MATLAB. So here, this is the Fiedler vector. And if I put the valuation or labeling, like the original labeling of the vertices, I have given 1 to 14. And then if I take these coefficients and put them, so it will look like this. So all vertices, they're getting a number. And depending on how the number is, we'll say that it's positive or negative or 0 vertex. And then V plus will include all the vertices which are positive or 0. So it contains all the vertices 1 to 6 because they're positive. And also it contains the vertex 7, 8 because they're 0. Similarly, in V minus, I'll put all the vertices which are negative as well as all the 0 vertices. So 7, 8. And then from 9 to 14, I'm putting here. So this is like you can see how they look like.
Excuse me, ma'am.
Yeah.
Ma'am, so you are saying that any vector orthogonal to all one vector will be parallel vector.
All one vector?
Any vector which is orthogonal to all one vector, that will be a parallel vector.
No, no. We can, eigenvectors are infinitely many, right? But we have one eigenvector, all ones vector, that is corresponding to 0. So if I'm choosing any vector corresponding to any other eigenvalue, that I can make orthogonal to my all ones vector. So I'm choosing a Fiedler vector and I have made it orthogonal to 1. Okay, that I can always do, right? Because that is independent of all ones vector. So I am just orthogonalized. So then my Fiedler vector means, in particular, you are choosing the eigenvector corresponding to AG, that is Fiedler vector. So that's an independent vector from all ones vector. So I'll orthogonalize it. So that can be orthogonal to all ones vector. So it contains some positive, negative, and 0. And okay. Because LG is a symmetric matrix, so we can have a set of orthogonal vectors, right?
Yeah.
Yeah. So this way we'll do the division that V plus contains all the non-negative vertices, V minus contains all non-positive vertices. Okay. So then this is like a main result we can say, which tells much more, and this is used to get the other result. So if you are taking a connected graph and x be any Fiedler vector of G, if I define this way like V plus, they are all the vertices which are non-negative corresponding to x. So x we are choosing one Fiedler vector. If you change x, your V plus V minus may change. We don't know now. So x is one Fiedler vector I have taken. You may have your multiplicity more, so you can get more vectors. So one vector if you are choosing, accordingly you take your V plus and V minus. And then this theorem tells that the subgraph which is induced by V plus means the vertices which are non-negative. So the subgraph induced by non-negative vertices that will be connected, and the subgraph induced by non-positive vertices that is also connected. So I'll show one part because the other part you can always show by multiplying the vector by -1. That will be again eigenvector, and that will come. So this V plus is connected. That also.
Ma'am,
So
one
as
thing I
yeah
wanted to ask. This Fiedler vector is an eigenvector corresponding to algebraic connectivity, right?
yes.
Okay. Thank you.
So X is a Fiedler vector, means it's the eigenvector corresponding to the algebraic connectivity. So it's I'm choosing it orthogonal to 1. So X is orthogonal to 1. And then your V plus and V minus both will be non-empty because the vector is non-zero vector. So it has some positive entry, then it has some negative entry. So your V plus and V minus both will be non-empty. Okay. So now, without loss of generality, let us take the first R vertices like 1 to R. They are belonging to V plus. That is that always we can rename the vertices. So I'm saying that 1 to R, they are lying in V plus. Okay. And then if possible, like let's say like we are going to prove that V plus will be the graph induced by V plus that will be connected. Let's say it's disconnected. So the subgraph which is induced by V plus, the vertices which are 1 to R, if the graph I'll consider induced graph, I'll consider taking the vertices 1 to R of G. And then let's say that is disconnected. So in that case, then I'll just take two sets, like let's say 1 to S and S plus 1 to R. These are the two sets I'm making. Disconnected means it can have more components also, but I'm just taking two divisions, let's say, and there is no S between them. So these may contain also more components, but I'm making like two sets, and there are no S's between this and this. So basically, I divided into two disconnected components, means not component, two disconnected graphs. So if that subgraph induced by V plus is disconnected, we are just thinking that let's say we are taking union of two graphs. And the first graph contains the vertices 1 to S, and the second one is containing S plus 1 to R. Okay. In that case, my matrix LG I can express in this way, like L11, L22. So L11 basically the graph which is induced by 1 to S. And L22 is the subgraph of G that is induced by S plus 1 to R. So, and they don't have like any connection. So here it will be 0 and 0. And from 1 to S, there can be connection to other vertices from those are R plus 1 to N. So here maybe because the graph is connected, so from here there will be certain entries which are non-zero. And then you can have also L23 that has certain entries non-zero, otherwise it will make disconnected. And then L33 that is obviously there. So your matrix will look like this. So LG can be described in this way. Here you will put 0 because these two are the disconnected ones. Now then, because X is the eigenvector corresponding to AG, so as per the block done in your LG, accordingly I am dividing my X as X1, X2, X3. So X1 basically is up to S, and then from here S plus 1 to R, and then here X3 R plus 1 to N. So that way we are taking the division, means just partition your vector. Okay. So this into this is giving you AG into this vector because this is the Fiedler vector we have considered. Now, as you observe, like this part is containing your all means all the coefficients must be in x1 and x2, all the coefficients must be greater than equal to 0. Okay, because that way you have made the thing. And in x3, all the coefficient lying which are less than equal to 0. Right? Because this part is 1 to R, that is corresponding to your V plus. So these entries are all non-negative. And here they can be non-positive in X3. Okay. Now if I look at the first equation, so that is L11 x1, L13 x uh, L13 x3, that will give me AG into x1, right? So this is your first blocked row you are multiplying, and the first system is coming this. Now here, if you observe, as I told, L13 must be less than equal to 0, because less than equal to 0 means it's a matrix with entries less than equal to 0. That's because here you will have some minus ones and zeros. So this is a matrix which is a non-positive matrix. So I'm putting this symbol. L13 is less than equal to 0. That means the entries are less than equal to 0. Similarly, X3, that is sorry, x3 will be here I may be missing. So x3 will be less than 0. Okay. Thanks. It's not less than equal to 0. And then we have L13 into x3, that will be greater than equal to 0, because these both will be multiplied. So that will give you L13 x3, that will be greater than equal to 0. So this part is greater than equal to 0. And then since G is connected, you have L13 must contain some entries, okay, non-zero entries. So this tells that L13 x3 must be not equal to 0. Okay, so I think x3 should be less than 0. That's containing all the negative vertices. So this is not equal to 0. This tells that if I just take to this side, so I'll get that L11 minus AGI x1. So I'm bringing this to this side, that equal to negative of this, and this is greater than equal to 0. So, and not 0. So this will be less than equal to 0, means it's a vector which is having entries less than equal to 0. And this vector again not equal to 0, because this is not equal to 0. And this implies that if I take x1 transpose and this vector, if I multiply, then this will be also less than equal to 0, because your x1 transpose means x1 is a non-negative vector. So if you are multiplying, that will again become less than equal to 0. And then you have, sorry. So that x1 transpose L11 minus AGI x1, that is less than equal to 0, that we observe. And that is not equal to 0 also, and less than equal to 0. But now I'll see whether my matrix is positive semi-definite or not. So my claim is this matrix will not be positive semi-definite. So if I assume that this is positive semi-definite, then for every vector this thing happens. And in particular, I'll choose x1. So x1 transpose L11 minus AGI x1, that must be greater than equal to 0. But we already obtained that x1 transpose L11 minus AGI x1 less than equal to 0. So both will conclude that this will be equal to 0. But this cannot be equal to 0. That we proved also, because this quantity is same as your L13 x3, and that's not equal to 0. So this cannot be equal to 0. So that will be a contradiction. So this matrix is not a positive semi-definite matrix. Okay. So what I can conclude, that because this matrix is not positive semi-definite matrix, so its eigenvalues are not greater than equal to 0. So there can be negative eigenvalue. So in that case, then it's telling that because I'm taking L11 minus AGI. So it telling that L11 has one eigenvalue less than AG. That will make negative for this. So L11 must be having one eigenvalue that is less than the algebraic connectivity. And then similar way, like what argument I use for L11, you can see L11 and L22 both are behaving same way. Okay, so I can make the similar, like I'll take this equation and then I can conclude that L22 also having one eigenvalue that is less than algebraic connectivity of G. So both L11 and L22, they are having one eigenvalue which are less than the algebraic connectivity of G. In that case, this matrix, if I consider L11, L22, and 0, 0, this is a diagonal matrix. So this matrix must have the second smallest eigenvalue mu that is less than AG, because it has L11 has one eigenvalue less than AG and L22 has one eigenvalue less than AG. So the second smallest eigenvalue, let's say that is mu of this matrix must be less than AG. Okay. So now, if I apply the interlacing theorem, this is a principal submatrix of your original Laplacian matrix. You can see your Laplacian matrix you had written in this form. So this matrix is a principal submatrix of this. So then if I use interlacing theorem, I think Rajesh sir has already told you. So if you are taking a principal submatrix of the original matrix, like symmetric matrix, then eigenvalues will interlace. Okay, that theorem is for like you are taking n minus 1 cross n minus 1 submatrix, but it can be applied again and again, and this way the eigenvalues will be. So the lambda 1 that is for LG, that is our 0, and then mu 1 will be the smallest eigenvalue of this that will lag, and then the next eigenvalue will come AG, and here the second smallest eigenvalue will come after that. So AG must be less than equal to this mu, okay, by interlacing theorem. So that gives a contradiction that you got that you have one eigenvalue, means second smallest eigenvalue of this is less than AG, but by interlacing theorem, AG must be less than equal to mu. So that's a contradiction. So what we assume that if I'm taking the induced graph corresponding to the vertices in V plus, that must be that is disconnected, that we assumed and we proceeded, so we got a contradiction. So our contradiction means assumption was wrong. So this, the subgraph induced by V plus, that must be connected. Okay, and in a similar way you can show that B minus is also connected, but also you can take like I had taken X and which vertices were lying here in V plus. If I multiply just X by minus 1, then those vertices will lie, like it will change, like B plus will become B minus and B minus will be B plus. So from that also you can conclude that B minus is also connected. So it can be proved. So this is one of the important results that will be used now to conclude the other things. So if your Fiedler vector is there and you are considering the subgraph which is induced by the positive, means non-negative vertices, that must be connected. The subgraph induced by the non-positive vertices, that must be connected. That you can see also in your picture. That if I consider this part, this is a tree, so this part is connected. And if I consider this is also connected. Nicely here means negative vertices, which if you consider, that is also connected. That happens for this graph, but this will not happen always. Okay, so then here the another thing that is we'll go for the classification of trees. So as we observe, like if you are taking a tree and then the earlier result that I had told, this is for any graph, and if I go, this is for any graph, okay. Now, if I take in particular, the example I gave is for a tree. If I go for tree case, so here we can classify the trees into exactly two classes. So, so let us consider a tree and X be a Fiedler vector. Okay, so it's an eigenvector corresponding to the algebraic connectivity. Then I'll divide similarly. Let us first suppose that X has no zero coordinate. This may happen if you have your eigenvector without zero coordinate. That may happen for certain trees or certain graphs. So first case I'm considering, let's say X has no zero coordinate. So either it has positive coordinates or negative coordinates. So then in that case, V plus will be containing all the vertices which are positive, and B minus is containing all the vertices which are negative. Okay, so then by the earlier theorem, B plus B minus both are connected, so they must be trees also, like in your example you show that contain zeros, but another example I'll give maybe later. You can see only positive and negative vertices. So in that case, B plus B minus must be connected, so they will be again subtrees. So in that case, you can observe that because positive vertices, they are forming a connected part, and then the negative vertices, they are forming a connected part. So you can observe that precisely there will be one edge which has a positive end vertex and a negative end vertex. Okay, and that's called the characteristic edge. Okay, and you can observe that will be only exactly one edge. Okay, because if I put two edges, let's say in between, then if I consider the positive vertices, then it will become disconnected because I have to take up from other way around, right? You can, I don't have here picture, but you can imagine, let's say two edges you are taking in that like positive and negative ends. So when you will consider set up all positive vertices, then obviously you have to like leave certain things. So it becomes disconnected. So it happens that you will get exactly one edge which has a positive end and a negative end vertex. So this edge is known as the characteristic edge with respect to the vector you have chosen X. Okay, so if you change the vector, it may change, but we'll show that that will not change. But I'm starting with one vector, Fiedler vector, and it has no zero coordinate. Then you have only positive vertices, negative vertices, so you divide it. And then you can observe that because B plus is connected and B minus is connected, so there will be exactly one edge which has a positive end vertex and a negative end vertex, and that's known as the characteristic edge of the tree. Okay, so this is the case where we are thinking that X has no zero coordinate. Okay, but it may happen that some some tree, like you are considering the Fiedler vector and it has zero coordinate. Then what will happen that let's say X has a zero coordinate. Okay, so in that case, if you look at the characteristic equation, and then this is like LTX equal to ATX. So from this, if I consider the ith equation, okay, so that will look like look at this. This is the Laplacian. So you will get that degree of that ith vertex. So dixi minus like you will get the minus ones into xj. So those will be coming as this sum. So how many vertices I will be adjacent, those will give you x's, and those will be added here. And the right side will be atxi. So I'm taking this to one side. So you will get like dixi minus atxi, and this side is containing one is getting multiplied with x if like j in the corresponding vertex j is adjacent to xi. So you will get from this, like if I consider the ith equation, you'll get this equation, right? So now if I say that there is a zero coordinate, so let's say that is xi, so that way I have taken the ith equation. So if xi becomes 0, okay, then your right hand side is 0. That tells that this sum is 0, means the vertices which are adjacent to I, for that if I add all the coefficients xj, that gives you 0. Okay, that means xj is 0 for all vertices which are adjacent to I. Then this sum can be 0, means all xj for which j is adjacent to I. If all are 0, then also this sum will be 0. or it may happen that I is adjacent to a positive vertex as well as a negative vertex. Okay, then somehow like some positive, some negative, and this sum can be 0. So either this thing happens that all the vertices which are adjacent to I, the corresponding coordinates are 0, then all this sum will be 0. That is your first case. Or it will happen that I must be connected to a positive, means adjacent to a positive as well as a negative. There can be more also. Okay, but this case can happen that one vertex at least will be adjacent which is positive and one is negative. So this is the second case. Okay. Now, if let's say this is adjacent to all vertices which are 0 vertices. Okay. So then I can go for another 0 vertex, and for that this thing can happen or this thing can happen. If this thing will happen, then all vertices adjacent to that vertex also 0. That way, if this case is happening for all vertices, then it will cover all vertices and I'll get zeros only. So that's a contradiction because your x is a non-zero vector. So for some vertex which is 0 vertex, this second case must be true. So one 0 vertex will be there, at least one, and that will be adjacent to a positive vertex and a negative vertex. Okay, and that vertex we call as the characteristic vertex. Okay, so first case I told that there is no 0 vertex. In that case, we'll find exactly one edge, which will give you one end vertex as positive, one end vertex as negative, and that's known as a characteristic edge corresponding to that vector. And if there is there are 0 coordinates, then we got that at least one 0 vertex will be there, which is adjacent to a positive vertex and a negative vertex, and that will be called as characteristic vertex. Okay, so here we don't know this is exactly one or more, but we can conclude this will be also exactly one. The earlier case, characteristic edge is exactly one, that is coming from the discussion. But here we don't know whether such vertex like which is adjacent to a positive and a negative and itself is a 0. So that vertex is unique or not. So, but that kind of means if such vertex is there, that's known as characteristic vertex. So it is clear that a pendant vertex cannot be a characteristic vertex because for a pendant vertex, it's adjacent to only one vertex. So it may be positive, negative, or 0, but we are defining characteristic vertex as a 0 vertex, which is adjacent to a positive vertex and also adjacent to a negative vertex. So a pendant vertex cannot be a characteristic vertex. Now, this theorem is telling that let's you are taking a tree and you are considering a Fiedler vector, and let's say I'm thinking that it has 0 coordinates. Okay, so and I'm assuming that n is a characteristic vertex. Okay, the last vertex. So always you can change your ordering. So without loss of generality, I'm assuming that n is the characteristic vertex. N is one characteristic vertex. Okay, so now if you consider just delete n and consider the components, okay, obtained from t minus n. So delete the vertex n, then because it's a tree, so it will be disconnected. So you'll get many components. So let's say t1 to tk are the components of t minus n. Okay. Then this result is saying that if you consider the vertices which are belonging to Tj, okay, for j equal to 1 to k. So any component you are considering, then it will contain all vertices as positive or all vertices negative or all vertices 0. So if your characteristic vertex you consider and delete that and you are getting the components, then all the components will behave like this. They are containing all vertices positive or all vertices negative or all vertices 0. Okay. So this I'm not proving. If you want to go for the proof, you can see like in the paper by Fiedler and also in Mary's paper it has been mentioned. And it's also appearing in Bapasar book, so you can check. So as a corollary, you will get this, that if you are taking a tree and X be a Fiedler vector, then T has at most one characteristic vertex with respect to X. So here also, like as I told you from the last discussion, we could not conclude that characteristic vertex is unique. But using this result, this theorem, we can conclude that we can have at most one characteristic vertex. So if a tree is there and you have a Fiedler vector which is containing a zero component, in that case, you will find out exactly one vertex which is adjacent to a positive as well as a negative vertex. How that you can observe? So if I assume that, let's say there are two characteristic vertices, okay? So that means I'm saying that, let's say I and J both are different vertices and they are characteristic vertices. Then what will happen, that I'm saying that xi must be 0, xj must be 0 because they are characteristic vertices. Now, if I consider the components of t minus I, so they are either positive or negative or 0. Like each component contains either positive vertices or negative vertices or 0 vertices. So the component which will contain j, okay, so in t minus I, the component which will contain j, that will, because j is xj is 0, so that j is a 0 vertex, so all other vertices in that component must be 0. Okay, so j is then not connected, means not adjacent to any positive vertex or negative vertex. Okay, so that's a contradiction. So j is not a characteristic vertex. Okay, so this way you can argue that if the second case occurs, means x has a component which is a 0 vertex, then like there will be one characteristic vertex in the tree. There cannot be more than one corresponding to this vector x. Okay, so two cases occurs for tree, and that there is either a characteristic edge corresponding to a Fiedler vector, or it may happen that there is a characteristic vertex corresponding to the Fiedler vector. Okay. Now, another thing is like that also tells like looking at this characteristic vertices and characteristic edges, like if there is a characteristic vertex in the graph, means in the tree, or if there is a characteristic edge in the tree, we can also relate it to the multiplicity of the algebraic connectivity. That also decides whether there will be a characteristic vertex or characteristic edge. Okay, for that I'll use this result to prove certain result. So let A be a symmetric matrix, and let's say GA be the graph which is associated to A. A is a symmetric matrix, so it can have certain non-zero entries we can take. If we are taking zero matrix, we cannot define like it will correspond to a empty graph. So A has certain non-zero entries and it's symmetric. So GA is the associated graph with A. That means this has n vertices if A is n cross n. And two vertices, they will be adjacent if the corresponding entry here, ijth entry, like ij will be like adjacent if aij is non-zero. That way the graph is defined. So it's a very simple way, like you look at the matrix and for the non-zero entries, the corresponding vertices will be adjacent. So that's the graph associated with A. Okay, so if that associated graph GA is a tree and A into this all ones vector is 0, that means row sums are 0 of A, then rank of A is exactly n minus 1. This is a more general result that then the we read, means we in the first lecture I told about, like if there is a tree and we are taking the n minus 1 cross n minus 1 sub matrices of the incidence matrix, they will all have full rank. So here this is a more general kind of. So this is also true if you take complex matrix. Here we are using symmetric. It's true also for Hermitian case. So if A is a symmetric matrix and this GA, that's associated graph, is taking a tree structure, so it becomes a tree. And suppose that this happens, that all row sums are 0. then your rank will be n minus 1. I'll use this to prove that if you are given with a tree and there exists a field vector with no zero coordinate, then your algebraic connectivity must be of multiplicity 1. So there exists only one field vector, means its multiplicity AG has multiplicity 1. So this is a interesting thing, and using this only we can divide your tree class to two subclasses. So if there is a field vector without zero coordinate, then you can always say that AG means AT has the algebraic connectivity has multiplicity 1. Okay, so that we can prove using this result. So let's say I'm starting with LT y equal to ATY. This is the field vector, and we are assuming that it has no zero coordinate. So all yi they are not zero. Okay. Now form one diagonal matrix E, and that taking the diagonal entries as coefficients of this y. Okay. So it's a diagonal matrix. And form the matrix C, that is you are multiplying E to LT minus ATI in both sides, left and right. So this is the new matrix C. Okay. Then you can observe that the graph corresponding to C, because the graph corresponding to like LT was a tree, and now you just multiplied, and here you just put up the diagonal entries, right? And then you multiplied the diagonal matrix in both sides, so this C will be again a tree. Okay, so the graph associated with C is a tree, and the way we have done this, you can observe that if I take the row sums of this matrix, that those will come as 0. So C into 1 will be 0, because this part into 1 is 0. Okay, and this part into 1 again will give you 0, because you have taken E, and this is a vector which is orthogonal to 1, and this E into 1 then will be 0, because Y into 1 is 0. Y inner product 1 is 0. So this into 1 will be 0. Okay, so this you can get that C1 is 0. So now using this theorem, you'll get that rank of C is n minus 1. Okay. So if rank of C is n minus 1, I can also conclude that rank of LT minus ATI, this rank will be n minus 1, because the way you can see, C is nothing but you just multiplied this diagonal to both. So rank of C is same as rank of this, so this will be again n minus 1. So you got that AT, because if I take AT multiplicity is more, then this matrix rank will decrease, right? So this has exactly rank n minus 1, that means AT has multiplicity 1. So if you are starting with a field vector and it has no zero coordinate, you can say that it's the only vector. That means AT has algebraic multiplicity 1. And the second thing is if you are taking a tree, and let's say xy both are field vectors, and I be the characteristic vertex with respect to x, then I will be the characteristic vertex with respect to y. Actually, once the characteristic vertex comes for one vector, let's say multiplicity is more than 1. The first case was multiplicity is 1. So in that case, characteristic edge appears. But the other case is there can be zero coordinate. In that case, we have not concluded what is happening, but we know that if I choose a field vector and that has zero coordinate, then there is a characteristic vertex, and that's a unique vertex. But if I change another field vector, it may happen that the characteristic vertex will be another vertex, because my valuation like coefficients may behave in different way. But this result is saying that characteristic vertex will not change. So the characteristic vertex will remain same for y also. So which vertex will be characteristic vertex for x, that vertex will remain same as the characteristic vertex for y. So it will not change. Okay. So this theorem I am not proving. But then we have these two kind of thing is happening. One thing is you have a tree where there is a characteristic vertex. Those trees are known as type 1 trees. And you can have a tree where the Fiedler vector has no zero vertex. So in that case also you know that there is only one vector, means the algebraic connectivity has multiplicity 1. That's so if the tree is having a characteristic case, you will call it type 2 tree. And any tree, as we observed from our discussion, so any tree if I am taking, that will be either type 1 or type 2. It cannot be both. Okay. So either this happens or that happens. And if algebraic connectivity has multiplicity more than 1, so we can conclude directly that it must be type 1 because it cannot be type 2, right? It must have characteristic vertices. And so if multiplicity is more than 1. But converse is not true. Okay. If it is type 1, it doesn't mean that uh, this thing will happen, that algebraic connectivity has multiplicity more than 1. Type 1, if it's type 1, if it's type 2, then algebraic connectivity has multiplicity 1. But if it's type 1, it may happen that algebraic connectivity has multiplicity also exactly equal to 1. Like, for example, you can look for the path of order 3. So the eigenvalues are 0 and then 1 and 3. In that case, the algebraic multiplicity has, an algebraic connectivity has multiplicity 1 because that is 1 is the algebraic connectivity. So 0, 1, 3 are the eigenvalues. But if you look at the path of order 3, actually the middle vertex that will, if you look for the eigenvector corresponding to the algebraic connectivity, that is 1, the eigenvector will be 1, 0, minus 1. So the middle vertex will be the characteristic vertex. So in that case, characteristic vertex is there, means the tree P3 is type 1, but its multiplicity is 1. If more than 1, we can certainly say that it's type 1. But if it's exactly 1, then it can be of type 1 or type 2. Now, this is another interesting result that, as I told, we are looking at negative, positive, and accordingly we divided into classes. But how the entries are behaving, that is also they behave nicely on the graph. So rather than reading this theorem, I'm going to. So as we observe, any tree I'm taking, it will be of type 1 or type 2. That means components may be 0 or no component will be 0. So both will keep. So first case is, let's say it's type 2. Then through the picture, I'll say. So this monotonicity result is saying that, let's say there is no zero vertex. So in that case, you have a characteristic edge. And due to the other results, like if you are taking the non-negative vertices, that will be positive and that will be connected. And if you are taking all non-positive vertices, that will be connected. So if there is no zero vertex, so basically you are taking all positive vertex that will be connected, all negative vertex that will be connected. So that way you can observe that if you have a characteristic edge that lies in the middle of the tree, that kind of thing is happening. I cannot say it's exactly in the center, but it's towards the center, that way. It depends on the tree structure, but it will lie in the middle. So here also you can see that the characteristic edge is this edge 7, 8. Okay, it has a positive end vertex and a negative end vertex. So 7, 8 is the characteristic edge here. Okay. Now, what the monotonicity property is saying is, if you start with a positive vertex and go along any path, okay, not including any negative vertex, that means you are going in this way. So if I start with 7 and then I went to 4 and then 5, you can observe that this coefficient, they are decreasing. The valuation or labeling you had given, taking the coefficients of this Fiedler vector, they are decreasing. So if you move along, starting with a positive vertex, you are going further. These entries will they will monotonically decrease. Okay, in any path you go. I think I have done mistake. somewhere. These two entries I have done mistake. I told the opposite. So if you start with a positive vertex, it will they will increase. Okay. So like here 0.0722. So next is increasing like this. So if you start with a positive vertex and move along, the entries will increase, monotonically increase. They may be equal sometimes. So they will increase. And if you start with a negative vertex and move without including any positive, so in this direction you are not going, so you will move along the negative vertices, then you can observe that they will decrease. So here, what is the value? This is less than that, like this. So this is the thing happening. Similarly, if you have the type 1 case, so you have in that case 0 vertices. In this case, if you start with a 0 vertex and then move, then it will happen that you may go to 0 vertex again. In that case, you will and all the vertices will become 0 in that path. Or if you are starting with a positive vertex and then moving without including that 0 vertex or in other paths, then the entries will monotonically increase. And if you start with a negative vertex without including 0 vertex, you are moving, so then you are going in the negative side. So then your entries will decrease. So that is the thing happen. So these two cases will happen. So one thing is you don't have a 0 component. In that case, there is a like unique case that has a positive end vertex and a negative end vertex. So that is a characteristic case. And if you start at U and you do not, while traveling, it doesn't contain V, and then the entries will increase. And similarly, if you start with the B and doesn't contain U, then the entries will decrease. And similar thing will happen here. If you start with a 0 vertex, then obviously you will find the complete component as 0. So the path will contain 0 vertices. Otherwise, if you are starting with a positive, then the entries will increase. And if you start with a negative vertex, the entries will decrease. So in the past lecture, someone was asking what is the purpose of studying. There are many applications, and the Fiedler vector, not only Fiedler vector, other eigenvectors, except the first one, that is the old ones. If I take other eigenvectors, those are actually we can form a matrix taking some k vectors, and then we can use that matrix in many practical applications, and that matrix is important, which is formed using the Laplacian eigenvectors. Okay, and while applying whatever the techniques they are using, those are known as spectral techniques. So there, it's not like adjacency eigenvectors we are using; it's Laplacian eigenvectors are mostly used. So not only Fiedler vectors, you can take any k eigenvectors. So I'll just tell you here one small example how the things are getting done, but it's getting done in like computationally for larger matrices and in many purposes. So one small example that I would like to give here. So this is one application, that is spectral graph drawing, we say. Okay, so embedding a graph on a plane or on a surface. So here what I have done is I have taken a bipartite graph. So it has 8 vertices and it's drawn in this way. So just a arbitrary graph I have taken. It's a 3 regular graph you can observe. So looking at the graph, I can observe it has 8 vertices, 3 regular, bipartite, like this. Now take the eigenvalues and look for the eigenvectors. Okay. So I just took the spectrum and nicely came all integers. In Laplacian case, many graphs comes with integer eigenvalues, and that's interesting. So here nicely, this is the spectrum. So 2 is appearing thrice. So this is the algebraic connectivity, you can see. So it has multiplicity more than 1. And then your other eigenvalues are like this. And I have taken the eigenvectors. So here, first vector is all ones vector, and then other eigenvectors I have taken. So you can observe this is a Fiedler vector. Here, 0 components are there. Okay, this vector is not with 0 doesn't mean that your characteristic vertices will change. This is a vector maybe I have taken that is a linear combination of these 3 vectors, so it's not taking any 0 vector, 0 value here, 0 coefficient, but you can get 0 coefficients. Okay, so I have just chosen because 3 vectors, so the linear combination has been made. So computationally obtained, so this will be. Okay, so I chose 2 vectors corresponding to the algebraic connectivity. So I have this red one and the green one I'm choosing. Others I have left, but you can take more also. I'll do the plane embedding, so I have chosen 2 vectors. Now take the 2 vectors, and because each has n components, and you also know that each component corresponds to a vertex, and so first component this corresponds to your first vertex like this. Here also you have n components, means here 8 components, and they correspond to the vertices, right? So then what I'll do, I'll take the first component from here and first component from here. So that will make a pair of 2 real numbers. So you got a pair of numbers. Okay, so that is corresponding to first vertex in both the vectors. Similarly, I'll take this coefficient and this coefficient, they correspond to second vertex, and I'll make a pair of numbers. Like this, I can have 8 pairs. So those are 8 points in the XY plane I can see because I'm taking real numbers. So these 8 pairs, the way the numbers are, I'll plot them. So you just plot as per the number value. So and then because each pair corresponds to one vertex, like this pair corresponds to 1, this pair corresponds to 2, like this. So now as per the adjacency in my original graph, I'll put the adjacency between them. In original graph, 2 and 5, they were adjacent. Here I made those 2 points adjacent. Okay. So now you see, and I just took the adjacency and I have drawn the graph. So the earlier graph was the same graph, this graph, but it was drawn in that way. And from the graph, we are not, means even we are not able to see what is happening. But now the graph is redrawn on the plane using the Fiedler vectors. 2 vectors I have taken, so it was drawn in plane. But if you take more vectors, you can also do in the surface. So like in more dimensions. So you can see this picture is obviously much better than the earlier picture, looking at like considering the graph. So that graph was if I look at that graph and this graph, this is a better drawing. So that way, like the things here happening, you can just see that the same technique is getting applied, and then the spectral technique that we say that is getting used for image processing. So this spectral drawing technique. So this is also used in image processing. Similarly, as I told, if I take the eigenvectors, some k eigenvectors, and form that matrix, then that matrix we can also like apply, and that is now getting used in artificial neural network to get the things, and also in more like data analysis kind of things. So the computer science people, they are using. So that way the graph Laplacian eigenvectors for a graph, those are much useful for the kind of work that is necessary currently. So like image processing and data analysis, all this. So this Laplacian eigenvectors are much more useful. But given a matrix, usually getting the eigenvalues is much more difficult. And then to get the eigenvectors, again, a difficult task. But sometimes we go for the eigenvectors and then we get the eigenvalues, because eigenvalues we get from polynomial, and solving a polynomial of large degree is not easy. So sometimes it's like, as I told, like in Laplacian case, already one eigenvector is known. So always we guess we take another eigenvector that is orthogonal to all one's vector, and then we try which eigenvector will work. That way, like for many classes of graphs, we know both the eigenvalues and eigenvectors. Okay, and those are helpful like for application purpose. So here I'll conclude giving 3 problems which you can track. So if I take a path of order n, and let's say n is odd, okay, then so that the central vertex will be the characteristic vertex. As I told in the path of order 3 case, the central vertex is the characteristic vertex. So here you take odd number of odd n and look for Pn, and show that the central vertex is the characteristic vertex. Okay, and in case of n even, you can guess then what will be the characteristic edge or vertex. Now the second question is if you are taking a connected graph and let's say x be a fielder vector. Okay, this side is not visible to me. So I have written, I think xi is greater than 0. So xi is a positive vertex. Then so that there exists a vertex j adjacent to I so that xi is bigger than x. Okay, so this you can also show. And this is a question that I would like to ask, that is it true that algebraic connectivity is necessarily decreases when a vertex is deleted? The same question I'll ask, that if you are taking a graph and then you are deleting one edge, whether algebraic connectivity will decrease. And same question, if you delete a vertex, whether algebraic connectivity will decrease. So both will depend on interlacing results. So you can observe what is happening. Okay. So here I'll end. I followed mostly these books by Bapot and Brouwer, and then Imris and Clavier for graph operations and products you can look, and you can also look for the spectrum of graphs obtained by using operations and products. And here some applications are there. You can see this book is a good book, but obviously high level a bit. But here applications are there. And this is the fundamental result that I told on algebraic connectivity. Those are all are in this paper, or you can see also some papers by Maris. So it contains. Okay. So any question you can ask.
Ma'am, algebra characteristic age for star graph will all the ages will be the characteristic age.
How can we?
Means this one characteristic age will be unique.
Characteristic age is unique.
Yes. So depending on that vector, it will change then.
No, it remains fixed. Na? Characteristic. If there is a characteristic age, then you have algebraic multiplicity of algebraic connectivity is 1. So only one vector is there. Okay, and that age will remain fixed. No, unique age. So in star case, it will not be age, right?
So star case, what will happen? That I want to be.
In P3 is a star, right?
Tree.
What
Star
happened? Central vertex is the characteristic vertex.
that vertex, but characteristic age.
Age नहीं होगा ना. Either this or this. So every tree is type 1
Okay,
or
okay,
type
okay.
2.
Yes, yes.
Ma'am, in one of the previous result that you have shown, that if T is a tree, then using some assumption you've shown that A of T has algebraic multiplicity 1. Can we say something about converse
Which one you told?
Yeah, this one.
This one is saying that if there is no zero coordinate, means characteristic edge is there, then algebraic multiplicity is 1 for the algebraic connectivity.
Oh, yes.
Mhm. And when algebraic connectivity is more, obviously the tree is type 1 tree. So their characteristic vertex will be there. Like stars, he was asking. For star, the spectrum is 0, and then 1 is appearing in -1 and -2 times. Okay, so algebraic connectivity for the algebraic, and the algebraic multiplicity for the algebraic connectivity is more. So in that case, for star, like I know, means I can conclude that it's a type 1 tree. So there will be characteristic vertex. Okay, so this case is when there is no zero coordinate. So there will be a characteristic edge, and in that case, multiplicity of the algebraic connectivity is 1. So only one Fiedler vector is there, and that will decide which is the characteristic edge. In when the other case is there, means characteristic vertices are there, in that case more Fiedler vectors are there. So what we observed, means what we proved is, even if there are more vectors, the characteristic vertex will be unique. That will not change. Like for star case, I can say the central vertex will be characteristic vertex corresponding to every Fiedler vector. Even the Fiedler vector n-2 Fiedler vectors you can get. But for every one, the characteristic vertex will be the fixed one, and that is the central vertex.
Yes, thank you. Got it.
Ma'am, algebraic connectivity is number. The number is giving the number of vertex you have to remove, then graph will be disconnected. If algebraic connectivity is 2, means that eigenvalues is 2, then we have to remove 2 vertex at least, then the graph will be disconnect.
ये कौन बोला?
No, ऐसा नहीं होता है ना?
ऐसा नहीं होता.
But ma'am, if for the complete graph, this n number of edges we have to delete for the edge connectivity. Sorry.
They are related. Means, as I told, algebraic connectivity is less than equal to vertex connectivity. Similarly, it's less than equal to also edge connectivity. So that way they are related, but not exactly it happened. Okay.
Yes, ma'am.
Like for trees, you can see the algebraic connectivity is less than equal to 1. Okay. Here you need only one vertex to delete.
Yes, ma'am. Yes, that how I have tried to do.
Okay.
Okay.